this is Binghao Ye, and here is my Lab 1 report. The aim of the lab is to observe the motion of objects moving in constant velocity. To do that, we have to capture a video of small car moving along a linearly frictionless trail, and we use the software tracker to analyze the motion, and we use the data analyzed by tracker to put into GlowScript to make a computational model, and we compare the results, which is the actual data and the model data. So the fundamental physics principle we use in this case is the Newton's second law, which means that a body remains at rest or in motion at a constant speed in a straight line unless it is acted upon by a force. In other words, by formula, F-net equals mass times acceleration. So if F-net is equal to 0, the acceleration is equal to 0. So it associates with our lab is that in modeling, we assume that F-net is equal to 0, but actually F-net isn't equal to 0, but it's very close, since we use a nearly frictionless trail. So we have to see the difference in velocity, which is compared to two graphs. So the result preview is that we can see there's a difference between the model and the actual. In the video preparation, we first put the small card into a nearly frictionless track and put a ruler in front of the track to set the scale and give the card a little push to make it move, and we record the video, and we use the software tracker to analyze the video to make X position versus time graph. So this is our video. This is how we're using tracker to analyze the motion. So we get the data from 0 seconds to 1.869 seconds. So this graph only shows partial data. To construct a computational model, what we need is the initial position. So in this case, we use the first row position X data, which is this number. And we have to find constant velocity. In this case, is the average velocity of the tracker data set, just to be accurate. And the time range should be 0 seconds to 1.869 seconds. And the formula we use in coding is the average velocity formula and the position update formula. Because in this case, it's no force applied, so we can safely use the formula. So this is the initial velocity and average velocity in code, and this is the position time update loop, and this is what the program looks like, and we can run the program. So we get the model data from this time range. Again, this only shows partial data. So we compared these two datasets and found that the directions of motion are the same, but the actual velocity is actually greater than that of modeling. So why there are differences? There are some explanations. First, the track provides friction and air resistance, so the F-net is not 0. But in modeling, we assume that F-net is 0. And secondly, the actual data is shifted due to mouse clicks and video frame related errors in tracker. So we might click the mouse too fast, and then the car just moving too fast. So it's actually faster than modeling. Discussion here. So about the first question, the answer would, the graph will flip too, since the car's direction of motion changes accordingly with the coordinate axis. So imagine that if we put the origin here and the car just moving like this in the negative x-axis, so it gains distance in negative way, so the graph should look like down. But if you flip the axis, the car which is moving like this gains distance in positively, so the graph will look like this. It's actually up, so the graph will flip. The second question, the answer is no, because it's impossible for the car in real life to have zero net force, so you can count these pushes and pulls. So there are countless surroundings interacting with the system in real life, from friction caused by the track to the particle in the air.